Hello, I'm James Floyd. We're going to continue working problems from Holiday and Resnick, Chapter 11. Chapter 11 covers rolling torque and angular momentum, and we'll be taking a problem from Module 1, rolling as translation and rotation combine. The problem that I've selected is number 2 from chapter 11, and it reads, an automobile travels 800 kilometers per hour, has tires of 75 centimeters diameter. What is the angular speed of the tires about their axis? B, if the car is brought to a stop uniformly in 30 complete turns of the tires without skidding, what is the magnitude of the angular acceleration of the wheels? And C, how far does the car move during the braking? The car is moving at 80 kilometers per hour, which is 80,000 meters per 3,600 seconds. Just cancel that out. And we'll just do this division right now. Equals 22.2 meters per second. So that's the linear velocity of the, this is linear velocity. And so they want to know the angular velocity. So we know V is equal to omega times R, which would go to omega equal V over R. The diameter is 75, so the radius would be 75 centimeters divided by 2, which would be 0.375 centimeters. And then we'll just convert that on into meters, which would be, okay, let's just do it. 75 centimeters is equal to 0.75 meters. And then when we divide 0.75 meters by 2, we get 0.375 meters. That's what R is equal. So we'll just plug this part A. V is, and that they're asking for omega, which is, omega is equal to 22.2 meters per second divided by our radius, 0.375 meters, and that will equal to 59.2, and this is radians per second. You can see here the meters will cancel, and all you're going to have is a dimensionless number, which will be radians per second. Okay. So this is part A. So we'll start with our kinematic equation. Omega squared final is equal to omega square initial minus, because we're decelerating, 2 angular acceleration, the change in theta. And we're going to solve for that. We know that this is equal to 0 because we're coming to a stop. So we're going to have, it's just going to go to omega naught squared. It's going to equal to minus, no, I'm sorry, it's just a plus now, 2 alpha change in theta. Now, we need to know what theta is. We have everything else. We don't have the angular acceleration, and we need to just solve for theta. So theta is going to equal 2 pi times the number of revolutions that the tire made, which is 30, and this is going to equal 6.28 times 30. It's going to equal 188.4 rads. So we have omega squared, which is 59.2, and that's going to be squared. It's going to equal 2 alpha, and we know we've computed theta, which is 188.4 rads. And so we're going to solve for alpha. So alpha is going to equal to 59.2 squared, 2 times divided by 2 times 188.4. And when we finish that math, we're going to get an angular acceleration of 9.24 rads per second square. So that's part B. Okay, C. How far does the car move during the braking? So let's just take advantage of the fact that our formula of S, which is B, the distance, is theta R. And we know which theta is. Theta is 188.4 rads time R, which is 0.375, 0.375 meters, is going to equal, put it right here, $70.65 meters. That's the answer to C. That completes that problem.